Hello, and thank you for joining the Peach Educational Session as part of the 2021 Virtual Southeast Regional Fruit and Vegetable Conference. I'm Sarah Scott, Extension Agent with Clemson Extension, and I'll be your moderator for this presentation. Pesticide CEU and CCA credits are available for most presentations offered during the live Southeast Regional Conference. Check the Pesticide CEU Guide for a list of approved presentations and also for participating states. The Pesticide CEU Guide is located in the Event Resources tab under the Media Player. The guide is also available at the Resources Center located on the main menu of the conference platform. Please note that pesticide credits will only be available for registered attendees and only during the live conference. Credits will not be available for any on-demand viewing. There's a simple three-step process in order to receive your pesticide CEU and CCA credits. First, go to the audience chat box, which is located on the left side of your screen. Type in your first name, your last name, and the states for which you are requesting credits. Again, go to the audience chat box located on the left side of your screen and type your first name, last name, and the states for which you are requesting credit. You will need to do this step for every presentation to request CEU credits. The second step is to sign out at the end of every presentation. In order to sign out, go to the audience chat box and type your first name, last name, and the states for which you are requesting credits. You will be reminded to sign out at the end of the presentation. And then the third step, you'll need to complete your pesticide CEU registration. You only have to do this step once during the conference. It's not required with every presentation. To access the pesticide CEU registration web link, open the Pesticide CEU Guide on the Event Resources tab located under the Media Player. The Pesticide CEU registration web link is located on the front cover of the guide. So this presentation is pre-recorded to hopefully reduce any technical difficulties. However, we will be answering your questions live at the end of the presentation. So you can submit at any point during this presentation by typing your question in the questions box and then pressing send. Don't forget to thank our 2021 conference sponsors and exhibitors by visiting them in the virtual trade show and the featured products pavilion. Lastly, don't forget to join us each morning for coffee chats and each evening for networking. You can check the conference agenda for more details on that. And now I'd like to introduce Dr. Joe Maja. He's going to be talking to us about using RFiD drones and Bluetooth to improve our plant inventory management.
Thank you, Sarah. The title of my presentation today is using RFiD, drones, and Bluetooth to improve plant inventory management. This is a collaborative work with James Robbins of the University of Arkansas, Tom Fernandez of Michigan State, Matt Chappell of the University of Georgia, and James Owen of USDA ARS in Wooster, Ohio. The project team also includes some key commercial partners from Avery Dennison. This work is partially supported by a grant from the Horticultural Research Institute, and my name is Joe Maja of Clemson University. Collection of plant inventory, such as count, grade, plant size, yield data, is time-consuming, often inaccurate and costly. Although improvements in the processes involved have been made, they still rely heavily on manual methods. In response to increasing labor costs and shortages, there is an increased need for adoption of technologies by the nursery industry. Growers are slowly adopting technologies such as the one shown below, the Green Atlas cartographer, which measures the height and count the trees, the famous plant spacing robots, and CHOP, our weeder robot, that automate or augment certain operations, but greater stride must be taken to integrate technologies into this challenging and structured agricultural environment. The overriding objective of this research effort is to develop and promote sustainable strategies that improve the profitability of the nursery industry. The specific objective of this project is to demonstrate merging specific ground and aerial-based technologies, such as the aerial-based unmanned system, RFiD, and BLE, in a whole system approach to address the specific need of providing on-demand plant inventory. Integrating production informations into the overall system will improve inventory data, irrigation management, and pesticide application. We developed two modules, the RFiD and BLE, that will be used as the medium of tracking plants or pots on the field. But for these presentations, I will only present the RFiD part. A quick overview of RFiD and BLE. RFiD is used for auto identifications for different objects, and it consists of two parts: RFiD reader or interrogator, and RFiD tags. There are three different tags commercially available: active, passive, and semi-passive. The passive tags do not have any power supply, instead use an incoming radio waves from the reader to power itself. We are using a passive tag for this project. BLE, or Bluetooth Low Energy, is a low-power wireless communication technology that can be used over a short distance. Note that this is a power device, albeit low-powered, and similar to RFiD, BLE needs a sort of an interrogator, except that the chip used for the interrogator is exactly the same chip as the one deployed as tags. A unique aspect of this project is to develop and conduct preliminary testing of BLE as a technology for inventory and to control other devices. This presentation is focused on preliminary efforts by a collaborative team which is trying to evaluate the use of small drones to collect plant inventory using these two technologies. The challenge for this team was identifying a RFiD reader that could be attached to a small drone. The left side of the screen shows the RFiD reader, the custom-built reader frame, and an example of one type of RFiD tag provided by Avery Dennison. The right panel shows the drone, which is a DJI Matrice 600 Pro. The reader module was designed to handle two technologies, RFiD and BLE, without changing the base electronic hardware, which will make it easier for us to test both technologies. We only need to change the reader chip and upload a firmware specific to the reader chip. The reader module developed by this study is the ARM Cortex M4-based core controller from NXP. It also comes with a wireless transceiver from Holybro, a micro SD card socket, and a GPS module from GlobalTop. The reader module retained high-performance ARM Cortex and can be custom programmed to read the reader chip and employ different communication protocols to transfer data to and from the transceivers and GPS module. Specific to the RFiD is the reader chip M6E from JADAC with a 7 decibel patch antenna, while for the BLE is the NRF 52840 from Nordic Semiconductor. An off-the-shelf aluminum extrusion and an enclosure was modified to house the electronics. The power, switch, micro SD socket, transceiver antenna, RFID antenna, and the GPS connector were routed outside the box for easy access. The RFID antenna was attached to the box by aluminum extrusion bars. Space between the bottom of the electronics box and the antenna was chosen to provide clearance for connectors and yet not interfere with landing the SUAS or drone. We also developed a dashboard for the reader. The dashboard displays RFID tag informations on the computer screen. The dashboard was developed using a Java runtime environment. The main dashboard displays the tag informations in real time. Tag information such as GPS, Received Signal Strength Indicator or RSSI, the pace of the signal, Electronic Product Code or EPC, the number of bytes received, time the tag was read, EPC tag bytes, input voltage, RFID voltage, and temperature. Before going to the field testing, 2 laboratory experiments were conducted. The first one was the static assessment of tag scan rate, and the second was evaluating the tag using an experimental design. The first experiment was a static assessment of the 14 types of RFID tags as shown on the right side. The RFID reader and 14 tags were placed on a wood easel as shown on the left. In the first experiment, 2 factors were evaluated: distance between the reader and tag and orientation of the tag relative to the reader. 5 different distances were evaluated: 5 feet, 10 feet, 15 feet, 20 feet, and 25 feet. 4 different tag orientations were evaluated for each distance: upward, such as tag upper surface facing directly toward the receiver; downward, where the tag flipped over so the upper face of the RFID tag is now pointing away from the receiver; horizontal 90 degrees sideways left, and horizontal 90 degrees sideways right. The RFID reader was placed in a stationary position in its side and elevated 2 feet above the floor, with the antenna pointing directly towards the tags. For each treatment, the reader was turned on for 6.5 minutes to collect tag readings. Experiment 1 was designed to screen 14 tags to determine those with the highest scan rate under lab condition. And based on that experiment, 4 tags with the highest scan rate were used. The experimental design experiment evaluated 2 factors: the tag type and tag orientation. Each treatment was scanned for 3 minutes in each block. To demonstrate how spread or cluster the data collection, the standard error equation was used to calculate the error bars. For field experiment, the RFID reader was attached to the underside of the drone or SUAS. There were 2 sub-experiments in the field. The first one was scanning tags while moving horizontally at a fixed altitude across tags on the ground, which we referred here as the vertically fixed or VF. And the second one is holding the same horizontal position over tags and then scanning tags at 3 different altitudes. We refer that one here as the horizontally fixed or HF. The field experiment was designed to evaluate the scan rate of 6 tag design when the aircraft would fly back and forth at a fixed height over tags on the ground. 2 factors were evaluated: the altitude of the drone and tag orientation. The experiment was designed so data for all treatments could be collected during the same flight. The 3 altitudes evaluated were 15 feet, 20 feet, and 25 feet. 4 different tag orientations were used for each altitude: tag facing upward, downward, horizontal 90 degrees sideways left, and horizontal 90 degrees sideways right. To ensure that a complete experimental run could be completed using a single aircraft battery, duplicate copies of some tag design were used in this experiment. Tag used were 5A, BF, 5B, 2F, 59, 12, 81, and 6F. Tag 81 was included since it yielded a high scan rate in lab experiment number 1 when orientated sideways to the reader. These 8 RFID tags were taped to a 2x4 wood board in 4 different orientations. The tag designated in the upward orientations were 5A and BF, while for downward orientations were 5B and 2F. The tag designated for horizontal 90 degrees sideways left were 59 and 12. And lastly, tag 81 and 6F was designated at horizontal 90 degrees sideways right. Wood boards were placed 10 feet apart from each other in a parallel configuration. This is the result of the number of tags scanned in relation to orientations from experiment number 1. The horizontal 90 degrees sideways right had the highest number of tags scanned, while downward orientation resulted in the lowest number of tags scanned. In addition, orientation at horizontal 90 degrees sideways right has the highest error, while the horizontal 90 degrees sideways left had the least. The lower plot shows the summary of the number of tags scanned by distance. The distance with the highest number of tags scanned is at 25 feet, while 5 feet has the least number of tags scanned. The longest error bar is at 25 feet, while 10 feet has the shortest error bar. This is the result of the number of tags scanned in relation to orientations from experiment number 1. The horizontal 80 degrees SR has the highest number of tags scanned, while downward orientation resulted in the lowest number of tags scanned. So results in the top figure shows the summary of the number of tags scanned by orientation. The horizontal 90 degrees SR has the highest number of tags scanned, while upward orientation is showing the least number of tags scanned. Downward orientation is showing the longest error bar, while the horizontal 90 degrees sideways right has the shortest error bar. The figure below shows the summary of the number of tags scanned by distance. So the distance with the highest number of tags scanned is at 5 feet, while 25 feet has the least number of tags scanned. In addition, 25 feet showed the longest error bars, while 5 feet has the shortest. The standard error difference between 5 feet and 20 feet is less than 2 bars. The result of the RCBD orientation table shows the standard deviations in the p-value of the tag names, 9F, 6F, 5B, and 12, on the data collected. Each tag orientations were scanned at a distance from 5 feet to 25 feet, and tag name 9F and 6F returned an insignificant result, and all 4 orientations. Moreover, tag 5B and 12 at upward and horizontal 90 degrees sideways right orientation produce a significant result. The result of the RCBD distance table shows the standard deviations in the p-value of tags 9F, 6F, 5B, and 12. In each distance, tags were scanned in all 4 orientations, and the following tags generated a significant result. At 10 feet, both 6F and 5B at 15 feet and tag 12 at 25 feet. These figures summarize results for the number of tags scanned while the reader is in a dynamic position based on distance and orientations. Take note that the reader here was already attached to the drone, or SUAS. Tag 2F at downward orientation shows the highest scan rate, followed by tag 59 at horizontal 90 degrees sideways left. Then tag 5A and 5B at upward and downward respectively. In addition, tag 6F at horizontal 90 degrees sideways left has the least number of scan. The downward orientation shows the longest error bar, while the horizontal 90 degrees sideways right has the smallest error bar. Furthermore, on the distance between the reader and the tags, 20 feet has the highest reading, followed by 15 feet, then 25 feet. 20 feet altitude is showing the longest error bar, while 25 feet has the shortest error bar. This figure summarizes results for the number of tags scanned while the reader is in a static position based on distance and orientation. Tag 81 at horizontal 90 degrees sideways orientation shows the highest scan rate, followed by tag 5A at upward position. Tag 12 at horizontal 90 degrees sideways left. In addition, tag 6F at horizontal 90 degrees sideways left has 0 readings. Moreover, horizontal 90 degrees sideways right orientation is showing the longest error bar, while the downward has the shortest error bar. On the distance between the reader and the tags, 15 feet altitude has the highest reading, followed by 20 and then 25 feet. 15 feet altitude is showing the longest error bar, while 20 feet has the shortest error bar. Our findings confirm that the two orientations that affect the scan rate of the tags are the upward and horizontal 90 degrees sideways right, where horizontal 90 degrees sideways right also reveals to have the highest scan rate. There is no significant effect on all tags at downward and horizontal 90 degrees sideways left orientation. The study shows that there are more tags designed, scanned, when the SUAS or drone was in motion as compared to when the drone was in place. This research concludes that the RFiD tag sensor patterns in the design perform differently in a diverse state. Some of the tag design scan rate efficiency was very low, while other tags are 95% more efficient compared to the other tag design. Here's a video of a short demonstration of our system scanning tag on the field. Thank you very much, and I will be happy to answer any of your questions.